Hello everyone, my name is Tony Ha. Today I'm excited to present our work titled HVPUNet, Hybrid Voxel Point Cloud Upsampling Network. This is a collaborative work with Vibhash Kumar Bhatt, Sunhung Jung, Alimur Reza, and David Crandall. Our research tackles the problem of point cloud upsampling, generating denser points to make 3D scenes more complete. This task faced several key challenges. First, upsampling large point sets can be computationally expensive and memory intensive. Second, existing methods usually use a fixed upscaling scale without adapting the level of detail in the scene. Third, it is also difficult to control artifacts such as overfilling and underfilling. In related works, two main approaches exist: point cloud-based and voxel-based methods. Point cloud-based methods such as GradPU, RepKPU, and PUDM directly generate more points with fixed scales to densify a 3D scene. Voxel-based approaches like those built on top of Minkowski engine densify 3D scenes through generative sparse convolution operations. Let's compare the methods built from two different representations. Point clouds store continuous 3D points in an unstructured format. They are memory efficient and precise, but require complex operations. Voxels, in contrast, store discrete occupancy in structured grids. They enable fast computation, but waste memory on empty space and lack in precise and continuous positioning. To combine their strength, we introduced the sparse hybrid voxel, which store both occupancy and offset information in the sparse tensor. This gives us fast processing, compact memory usage, and precise location. In practice, a hybrid voxel is stored as 4-channel sparse tensor, 1 for occupancy and 3 for offset. Building on hybrid voxel, we propose a hybrid voxel point cloud upsampling network. Our model performs two sequential tasks: shape completion and super resolution. The shape completion initially imputes the missing geometry from sparse points. Then the super resolution further refines the 3D scenes by upsampling the voxel resolution. Our network takes 4-channel hybrid voxel as input, expanding the receptive field through operational voxel expansion, and outputs 8-channel sparse tensor. The outputs include, first, 3-channel unsigned distance field for implicit geometry learning and voxel pruning. Second, 1-channel occupancy for binary indication whether each voxel is occupied or not. Third, 3-channel offset vector field to provide sub-voxel precision and implicit learning. And lastly, 3-channel normal vectors for surface of orientation learning and surface reconstruction. This diagram shows how our model performs shape completion and super resolution in the hybrid voxel domain. Unlike point cloud methods that upsampled points by fixed ratio, our voxel formulation allows dynamic densification, producing more or fewer points depending on the level of details in a given region. This dynamic densification helps reduce both overfilling and underfilling issues. Here we visualize how we reconstruct the ground truth distance fields for supervision. The unsigned distance field encodes absolute distance from occupied voxels, while the offset vector field captures signed distance from each voxel to true surface, allowing precise geometrical reconstruction. Earlier 3D generation methods using sparse voxel rely mainly on downsampling and upsampling layers to expand generative regions. We propose operational voxel expansion, which directly increases candidate voxel regions for reconstruction. As shown here, using voxel expansion produces a much more complete 3D reconstruction compared to the models without it. We train our model using 4 different loss functions with equal weighting: occupancy loss using dice coefficient, unsigned distance field loss using L1 distance, offset vector field loss using L1 distance, and normal loss combining sine and L1 losses. These losses are applied across multiple resolutions to ensure stable learning. We evaluate the model performance on two standard data sets for point cloud upsampling called PUGAN and PU1K. For PUGAN, we test on multiple upscaling factors, while PU1K we evaluate on the highest upscaling factor. Compared to the existing point cloud methods, our approach achieves comparable reconstruction performance in both occupancy and point-based metrics, and shows dramatic improvement in efficiency with much less VRAM usage and inference time. We further analyzed model stability on the corrupted inputs and the impact of each proposed component. The table on the left suggests our model shows stable performance across different types of the input corruptions. And the table on the right shows operational voxel expansion and voxel pruning help in robustness and overall performance. Finally, we visualize the reconstructed samples for qualitative analysis. On the left, we can see our method produces cleaner and more complete shapes with fewer overfilled or underfilled regions compared to the prior works. On the top right, we show normal estimation and surface reconstructions at the highest resolution. The estimated normals help generating fine quality surface reconstruction. On the bottom right, we show how surface reconstruction quality differ by different resolution in our multi-resolution outputs. Thank you for listening. If you have any questions or comments, please feel free to contact me at this email address.